All right, I hope you guys had a great weekend. Let me share my screen. Today we're going to be talking about waves and flooding. And sea level rise will appear in this lecture too. All right, so the topics that we're going to, I should mention that we have a guest listening in on Zoom today. Dr. Nancy Rabelais is listening in on Zoom. She's going to give me some constructive feedback on my teaching. And you will hear her name when we talk about coastal dead zones and low oxygen areas in coastal waters. So I think it might be interesting for you to know that she's listening in today. Okay, so today we're going to cover waves, erosion, seawall limitations and solutions, different types of flooding, and sea level rise. And the learning goals today are to understand, first of all, that ocean waves occur as a balance between gravity and a sea surface disturbance like wind, typically wind. We'll learn that the sediment that is carried in ocean water in waves acts like sandpaper, and over time it erodes even hard rocky shorelines. We'll learn that typical seawalls, which are just vertical walls, cause water to overtop the structure and erode on the other side, and they can scour sediment from the front of the wall, undermining their integrity. And we'll learn sea level rise from climate change, as well as other issues like land subsidence are major concerns for coastal residents, including major cities. And this image here is just a dramatization of flooded New York, meant to inspire concern for the impacts of sea level rise, because scientists anticipate that sea level rise will be a big concern for New York, as we will learn later on this lecture. Okay, so we have to start off with waves. Waves are a big part of the story of the impacts that coastal people experience from differences in water levels. And so let's do a little bit of review from OCS 1005, and hopefully I'll go into a little bit more depth here on waves. So ocean waves occur as a balance between gravity and a sea surface disturbance, usually wind. And so wind usually starts the pileup of water that forms a wave. And initially it forms as a ripple, which are called capillary waves. And then as more and more wind blows, as more and more wind energy is transferred into that water, the size of the wave increases, and typically if it's larger than a ripple, we call it a gravity wave. More wind energy can be transferred to the waves as the wind blows longer, and that would be increase in duration. As it blows further, which is fetch, or stronger. So that would increase the amount of energy that's transferred to the waves and make them larger. And the wind essentially pushes the water together into a pile. And as that water piles up, gravity will then draw the pile of water back down, and it overshoots in either direction, kind of oscillates back and forth. And those overshoots keep the cycle going. So the waves will be overly high, and then they'll develop some potential energy because of their height. And then they'll drop because of gravity, and that energy, the potential energy, is converted to kinetic energy of motion. And so in case you don't get too many exposures to physics concepts, here are these concepts here for you. So potential energy is the energy held by an object because of its position relative to other objects. So in this case, the highest point on the wave would have some potential energy because it's above sea level, and so it is impacted by gravity. And so that motion, once gravity pulls down, is converted to kinetic energy, which is the energy that an object possesses due to its motion. So it has potential energy, and then as it drops and accelerates downwards, that potential energy is converted to kinetic energy. All this to say, essentially, waves are formed by a balance between a force that piles up the water and gravity, which pulls it back down, occurring in an oscillation. Waves in the ocean move energy across the ocean surface. They don't move a whole lot of mass. They move energy. And so what happens to each water parcel as a wave passes through, as the energy from a wave passes through, is the water itself moves in a relatively small orbit and stays mostly in place. The deeper you go beneath the surface, you'll notice, at least initially, some impact of the wave energy passing by, but the orbits get smaller and smaller until eventually you get deep enough and there's essentially no impact of surface waves. As waves move across the deep ocean, they're not impacted by the bottom, but then eventually they're going to come to a shallower area, and as they move into shallower water, they will start to interact with the ocean floor. And that changes the movement of the water. You can see here these orbits are becoming compressed. They're becoming out of sync. And that is what happens as a wave starts to shoal. And so a shoaling wave is when surface waves enter shallower water. And as a result, they slow down and they increase in wave height. So you can see these waves are increasing in wave height in this image as they move closer to shore. When they increase in height enough, they'll become unstable, and that's when we notice the waves break. And so that's why waves break when they approach shore, because they're becoming too tall. As the waves come into shallow water and start to interact with the ocean floor, they can pick up sediment, and they'll often do this. You can see in this image here of this wave how sediment is being swept up into the wave, and some finer sediments will make it all the way up into the part that's breaking and crash onto shore. When sediment's picked up in water from a wave, that ocean water acts like sandpaper when it impacts a surface, and over time it can erode shorelines, even really hard rocky shorelines, even cement barriers. So if the waves are strong enough, if there's enough sediment available for it to pick up and move, these waves can have a large impact on shoreline erosion. The bigger the waves are and the more sediment they carry, the more erosion will occur. And this erosion occurs through abrasion, which is the process of scraping or wearing something away, just like sandpaper. Steeper beaches tend to have more powerful waves because the sudden depth change makes the waves dissipate their energy more quickly over a shorter distance. So they grow larger, quicker, and then crash quicker. And so all of that energy tends to be concentrated in a much smaller space. And so that's when we tend to see more powerful waves and potentially more impacts of abrasion. So we really care about all this when we're trying to figure out if a shoreline is protected from waves. And as we've learned in past classes, we do a lot of things to protect our shorelines from waves and from flooding, and one of the things that we like to do is build seawalls. And seawalls are an important tool in our toolkit. They will often fix the location of the coastline, but they are not perfect. And here is the main issue. They don't stop erosion. So we've learned how the beach in front of a seawall will disappear over time. So let's talk a little bit about how that happens now that we know a little bit more about waves. So we learn that seawalls don't arrest the ongoing erosion. On the contrary, sometimes they make the erosion worse on the seaward side of the seawall. This is especially the case when you have a vertical seawall that the waves just crash into. The waves are essentially encountering the steepest profile, a vertical wall, which causes the waves to break right as they hit the wall. It can cause water to overtop the structure and erode the other side, as you can see in this image here of eroded concrete from an area where waves overtop the structure and abrasive forces are wearing away the concrete. Also, water has to go somewhere, so as waves are crashing against this wall, they have to return to the ocean. The water has to go somewhere. And so the water will go down the seawall and return to the sea across the bottom. So you get some rushing water across the seafloor right at the foot of the seawall, and this can scour the sediment out from underneath of the wall. and erode the foot. And so you can see in this image, if enough erosion happens, you get water moving underneath the seawall and sand eroding away underneath the seawall, which will undermine the support. So we do know about these problems, and engineers have developed a variety of ways to create better seawalls that deal with some of these issues. And so here are some of those. Modern seawall designs that can dissipate wave energy on the approach or reflect wave energy. These are some possible solutions. You have a curved wall here, a stepped wall, a wall made of cement blocks, which also has these steep steps, or riprap structures, so those rocks which provide a rough surface that can break up the water. So what do some of these do? Let's look at the curved seawall. So what this is designed to do is deflect the water. So the water will rush up, impact the seawall, and essentially go up the seawall and be shot back out to sea through the air instead of through the underside of the seawall. So water is returned to the sea along the surface rather than along the bottom, and this can reduce the undercutting of the seawall and prevent the wall from being undermined, which is nice. These stepped or rough surface designs, these work the same way that you would expect, for instance, any structure like salt marsh or mangroves to work, where this roughness will dissipate the wave energy. Of course, it doesn't have all the same functions as a salt marsh or a mangrove, but at least it has some surface roughness that will dissipate wave energy before it hits the shoreline. And that spreads the energy dissipation of a wave over a wider area and reduces the potential for erosion. So these are some solutions that people much more smart in this realm than I have come up with to deal with typical erosion from a vertical seawall. I know we've talked a lot about flooding, and that's because it's very important in coastal areas, and this is a class on coastal oceanography, so it pops up a lot. So we've talked about flooding in previous lectures as it relates to tides and sedimentation in rivers, but I think it's worth, now that we've talked about waves, and since we're talking about sea level rise in this lecture, it's worth revisiting as its own concept now. So just to remind you, a flood in this course is defined as an overflow of water that submerges land that is usually dry. They're the most common and widespread natural severe weather event. And flood can take a variety of forms. So it can look really different because floods can cover anything from a few inches of water traveling across a surface, like you would get in typical flash floods in this area, to water of several feet kind of hanging around, flooding the first floor of structures. But all floods can be dangerous. Even a few inches of water can be very damaging and dangerous. In this image here, and as you probably know living in this region, even a few inches of running water can sweep vehicles off of a roadway. So these can be really dangerous to drivers. And of course, floods can happen during heavy rains, as is often the case in Baton Rouge. They can happen when ocean waves come on shore, when snow melts quickly, when dams or levees break. All of these things can cause floods. So floods can look very different depending on the circumstances that created them and depending on the circumstances of how the water is moving over surfaces. We do have some categories of different types of flooding that I think it's important to consider. So these are some basic categories of floods that are quite common. So riverine flooding occurs when relatively high water levels overtop natural or artificial banks of a stream or river. We certainly have to worry about that around here with the Mississippi River and its tributaries. Flash flooding is defined as an instance when runoff or drainage cannot adequately disperse intense rainfall. So this is when you have intense rainfall events, and that water has to go somewhere. There's no real efficient way to get rid of the water, and so it moves over the ground for some period of time. Sometimes it can move quite rapidly. It's usually caused by slow-moving thunderstorms. Dam or levee failure is relatively rare, thank goodness, because it can cause significant downstream flooding, and the water moves very fast. It carries a lot of structures, trees, sediment with it, so you get swift moving water and high amounts of debris. This image here, this loop video, is showing the moment that the Edenville Dam in Michigan failed in 2020, and this triggered catastrophic flooding. And so this is video of the initial dam failure. And this flooding carried away trees, it flooded towns for days, it drained an entire lake. I mean, it had some huge impacts on this area in Michigan. Storm surge flooding, which we've talked about when we talked about storms, occurs from a rising of the sea as a result of atmospheric pressure changes and wind. But I included it here because it's a type of flooding. Might as well have them all in one area. Same with tidal flooding. We've covered this in the past when we talked about tides. We also talked about how this is called nuisance flooding because it happens quite often, sometimes monthly, sometimes even more often, depending on the location. And it's a term used to describe minor flooding that occurs at high tide. Even though we call this minor flooding, it can still have really big impacts for people, as we know. And we also know that this type of flooding is becoming much more common and damaging due to sea level rise, though I'm going to go into more detail on that now. It's weird to watch a dam collapse like that. That's actually like more of a levee being undermined there. Okay, so before we move into sea level rise, let's go ahead and take our quiz. Quiz for today is a true-false question. So true or false, waves move energy long distances across the ocean surface. Water parcels themselves mostly move in relatively small orbits, staying mostly in place. True. Okay, so the answer to this is true. Good job, you guys. You did really well on this. So it's a hard concept to wrap your mind around, but waves, what surface waves in the ocean are actually doing is they're moving energy, sometimes across long distances, but the water itself is moving mostly in small orbits. And you'll know this if you've ever hung out in an area and like floated on the waves. You don't get transported to shore very quickly. You mostly stay in an area and bob up and down. So, good work. Okay, so let's talk about sea level rise. So we're going to finish off this lecture with a little bit on sea level rise. Sea level rise is an increase in the level of the world's oceans due to the effects of global warming. And I say global warming here instead of global climate change because there are two aspects of sea level rise, and they're specifically associated with warming. And these are added water from melting ice sheets and glaciers, which were on land, but as they melt, they contribute their water to the ocean. And the thermal expansion of seawater as it warms. So as a liquid like water heats up, the water molecules move further apart and you actually get an expansion of the water. This is a really big deal for humans. So in the United States, almost 40% of the population lives in relatively high population density coastal areas where sea level rise plays a major role and forms a major risk. And globally, 8 of the world's 10 largest cities are near a coast. You can see in this image, most of the largest cities around the world, these red dots here, are located in coastal areas. And these include New York, London, Buenos Aires, Mumbai, Bangkok, Shanghai. All of these locations are near the water and have to deal with some level of sea level rise. So this is a real challenge for humanity. Another aspect of the sea level rise that we observe from our location on the coast is actually the sinking of land. So land subsidence is a gradual settling or sometimes sudden sinking of the Earth's surface, and it occurs for a variety of reasons that are location specific, but here are the major ones. So it can occur when large amounts of groundwater have been withdrawn. So that would be, for instance, tapping into underground water reservoirs for drinking water supply. And when we do this, the rock will compact, actually, because the water is partly responsible for holding the ground up. And this can cause subsidence, and some of that subsidence can be relatively quick to happen. And this is when we see sinkholes form. So this is a major problem. For instance, in Florida, when you hear about all the sinkholes forming, oftentimes finger is pointed at water extraction as the cause. Another reason for land subsidence is post-glacial rebound, which is the ongoing movement of land that once had very large glaciers on top of it, which were very heavy materials. So after those glaciers melted, the land kind of has to get back in equilibrium. And even though the ice melted long ago, the land once under and around the ice is still rising and falling in reaction to that burden. So that's still happening. The land is generally rising in areas where glaciers were present and subsiding outside those areas. And so as you move closer and closer to, for instance, the equator, where glaciers weren't really located, then you might see some sort of land subsidence. And actually, the U.S. East Coast is a big location for land subsidence, and a lot of that is post-glacial rebound, as well as, of course, groundwater extraction. And this third thing here, so this is kind of a very location-specific thing, but I think it's relevant when we talk about the U.S. East Coast. So remember that meteor that we learned that formed the Chesapeake Bay? Well, that meteor is also responsible for subsidence in that region. So the impact of the meteor loosened sediment in the vicinity of the impact zone, and the land inside the crater is still settling. So this increases the movement of the land in terms of it sinking into the sea at the location immediately around the mouth of the Chesapeake Bay. You can see in this image all of these blue dots represent areas that are sinking, and some of the darkest blues are located around the mouth of the Chesapeake Bay. So all of these sources of subsidence add to the impacts of sea level rise caused by climate warming. So together, those two impacts will result in what kind of sea level rise you observe at a specific location. This means areas with a lot of subsidence are experiencing what seems like faster levels of sea level rise. Speaking of fast levels of sea level rise, I don't think that this lecture would be complete if we didn't talk about the Maldives. So the Maldives are an island nation just south of India, and it is a nation made up of islands. There are 26 ring-shaped islands that make up the Maldives, and they are coming to terms with climate change before the rest of us are, really, because they are the most vulnerable country in the world to sea level rise. So they have a long record of taking the lead on climate change, even though there aren't very many people and they're not a major power in terms of economic resources. They've taken the lead on climate change because it impacts them in a drastic way, and it's impacting them now. 3/4 of the land in the Maldives is no more than 1/2 meter above sea level. So 1/2 meter, that's 1.5 feet. That's not very much. The majority of the nation will be inundated by the end of the century, even under conservative estimates of sea level rise. So the land is disappearing, pretty much no matter what we do. The past policy of investing in seawalls and other infrastructure was deemed as insufficient. And that's because this nation is at risk of the impacts of waves like tsunamis, which can make short work of the concrete structures that they build to try and keep back the sea level rise. And so what the nation's leadership has done is they've established a fund that's mostly funded by tourism dollars that will help them move to a different location as a nation when it comes time to do so. That's how they have decided to deal with the impact of sea level rise on their nation. So they hope to preserve the culture by moving their nation somewhere else. This is probably going to be something that many locations have to deal with. They've identified a few locations that they might like to move, like Sri Lanka and India, because they have very similar cultures, so they think that they would fit in well there. And they've identified Australia because there's so much land available in Australia. And so it's ongoing, the decision about where they're going to move, but they're already raising money for this. And this event actually made headlines when it happened. So they, several years back, there was a very charismatic young president elected for the Maldives, and he was very good at publicity, very good. He held his first cabinet meeting underwater to publicize the risks faced by his nation, which I think is a very clever idea. What a cool photo op. Be hard to communicate, though. So as you can see from what's happening in the Maldives, humanity is really highly invested in understanding how climate change is going to impact them. So sea level rise being a major component of that, so they can adapt. In the case of the Maldives, that adaptation might mean moving to a completely different location. But it's good to know how bad sea level rise is going to get so you can have the time to raise the money that you can do those actions. So with continued ocean and atmospheric warming, it's estimated that sea levels will rise for many centuries, and that sea level rise will actually speed up. And so we can't really look at current rates of sea level rise and say, oh, this is how it's going to be in 50 years. So what we need is models to help us predict. So we've talked about how models can be used to make predictions. And in the case of climate change, the standard of models that we use to make predictions is those produced through the Intergovernmental Panel on Climate Change, or the IPCC. You've probably heard IPCC in the past. And this is the United Nations body for assessing the science related to climate change. So there are 195 member countries, thousands of experts from all over the world that contribute to the work of the IPCC. They're not paid for the work. They do it because it's important for humans. The countries will weigh in on the IPCC process and interpret the results. And new reports come out about every 6 to 7 years. The latest one was in 2019. The projections from sea level rise are made using multi-model averaging. So it's important to note, and as you'll see from today's activity, not all models, so no models are actually correct. Some models are actually useful because they approximate reality. And by using multi-model averaging, we can take the strengths of the models that we include in this set of models that we're averaging and minimize the weaknesses. Average results from multiple different models go into multi-model averaging, and they filter out, by averaging, any sort of bias and errors of individual models. Make it less likely that we're making decisions based on model error. And you can see here in this image the results from the IPCC sea level rise model. By the year 2100, if we look at these intermediate scenarios, which I think are a pretty good place to start, we can expect about 0.5 to 1.5 meters of sea level rise. Of course, this is location specific, because you might have some areas that are subsiding that see drastically higher levels of sea level rise, or even areas that are rising up in terms of the land masses, and that might see less impact of sea level rise. But that would be an average. Notice how the rates of sea level rise accelerate, especially after 2050. And that goes to show that it's going to be really hard to look at what's happening currently and make estimates about the future without looking at some of these models. And notice also in the extreme case of all of these model runs, we might expect over 2 meters of sea level rise. So that's over 6 feet. That's a lot of water. I think where I live right now, I'm 11 feet above sea level, and we know Baton Rouge is on pretty high ground. So, I mean, that's a lot of water. And of course, as I mentioned, this doesn't factor in land subsidence, which will make things worse for some locations. I also wanted to point out that the IPCC projections reflect the scenarios that are deemed most likely, and these are not the full range of scenarios that scientists think are possible. And so this red line, the extreme version, we'd like to think of that as the worst case scenario, but it's not even the worst case scenario. It's the worst case that we think is likely. So this is our best estimate as to what will happen. I want to be practical about it so people can prepare. All right, so at this time, I am going to send you into an activity to look at a model that's helping cities adapt to flooding. So go ahead and complete the Storm Sense activity in the 21 in class folder. And I only have a few slides left, so I'll go ahead and give you, let's go all the way to 11:15, and then I'll check in with you. How about that? All right, it's 11:15. We have 5 minutes left. Is it all right with you guys if I go over a couple of these answers? You can continue working if you want to. Cool. Cool, cool. Okay. So this gave you two examples of a way that a street level model can be used to help us estimate how water will impact coastal cities. And the examples were from Charleston, South Carolina, and Virginia Beach. And importantly, I wanted you to read this section where there's a saying that all models are wrong, but some are useful. So make sure that you think about that a little bit. You know, models are only as good as their ability to approximate reality. And we can figure out if they approximate reality by comparing model predictions or projections to some sort of real data that we have. And so that's exactly what's been done with these models. And so we know that they're pretty good, and we think that we can use them for a variety of purposes, but we're not going to be getting exact water levels out of them. We're getting predictions. So this first example is from a 12-foot seawall that people hope to build around Charleston, South Carolina. And you saw some simulations of how water moves across Charleston with the seawall and without. And so certainly the seawall would protect Charleston from a Hurricane Hugo-sized storm in the future. However, it probably has a lifetime of, maybe a couple of decades, but when we're reaching about 2100 because of predicted sea level rise, we expect that the sea level will approach the top of the seawall about that time if there is a similar storm surge. And it may even overtop it, which would be horrible. So a lot would have to do to keep that seawall current. And then for the Virginia Beach example, I wanted to point out that... Okay, so here we are. In this question here, this image shows the maximum extent of flooding, and the structures in red are the ones that were predicted to be flooded. And then you can get water depth at each point on this image if you wanted to. And I asked you what types of information can a city get out of an image like this. Choose all of the correct answers. And so an estimate of losses and damage due to a storm. Yes, you could probably do this because you've got specific buildings that would be impacted. So you could estimate what flooding would cost for all of those buildings. An estimate of the height each building would have to be raised. Yeah, because you can estimate what the level of the storm surge would be at each individual location. A way to prioritize funding for prevention. Certainly, because you can see which buildings are most likely to be impacted by a storm. But the exact water levels, not so much, because this is a model. So it's not giving you reality, it's giving you an estimate. So the exact water levels that occurred during Hurricane Matthew, those would have to be measured. We can estimate them using this model and compare those estimates to the measured values, but we're not getting out of this model exact water levels that occurred during the hurricane. So D was meant to be false. All right, I'm going to finish up with one last little aside. So this final slide is actually about a current event. And some of you might even decide to do this for your current event that's due in about a week. So this past week, I'm guessing that you've heard about the massive container ship that has blocked the Suez Canal for about a week. Yeah, right? Even if you've only heard about it from the memes, I'm pretty sure you probably know that this happened. So this ship crippled trade, and they really didn't know how to get it unstuck. So their best option, it totally did, and the tides helped. I'll show you how. So the ship they were going to have to unload all of the boxes from it, all the containers from it. It was going to take a really long time, and so this caused a lot of panic because we were looking at like multiple weeks that the ship was going to be stuck, and this crippled the global would cripple the global economy. But thankfully, scientists were hoping that an extreme tide that occurred last night would be high enough that it would allow the ship to float. It was a spring tide, so it was caused by the alignment of the moon and the sun, as we've learned. And it did allow the ship to float. So we can definitely thank the tides for helping us with this, catastrophe, essentially, or what could have been way worse. So yeah, I just wanted to bring that up. Super cool example of an oceanography concept in the news. And a great a great opportunity to share a meme with you. So I will end class here, and then we're going to have another lecture on Wednesday, and then Friday class is not being offered because it's Good Friday. So have a wonderful day.